In order to understand what the derivative is, I have here graphed the function x squared over 6, and please keep in mind that nothing on this graph is drawn to scale. What a derivative is, in the most simplest terms, is the slope of a line. But more specifically, it is the slope of a line when the change in y and the change in x are extremely small, infinitesimally small. So I've demonstrated the shrinking of the change in y and change in x over here on the right. And as you can see, the 2 points become closer and closer to each other. As this change becomes even smaller, the slope of this red line is the derivative at the point A. Now, to explain the notation, in the numerator here we have f of a plus h minus f of a. That essentially is the change in y, as you can see here. The denominator is a plus h minus a, which I have denoted over here. That essentially is the change in x. So if you remember, the slope of a line is the change in y over the change in x, y2 minus y1 over x2 minus x1. The f of a plus h is y2, the f of a is y1, and the a plus h is x2, and the a is x1. Essentially what we've done is we've started with a and we've added on a distance to a. That distance is h. So we are out a distance of h from a. What we do is we say that we take the limit as h approaches 0. In other words, we're going to take that distance h and shrink it down very, very close to a. So the distance essentially becomes very, very close to 0, but it's very important to keep in mind it will not equal 0. Now that same concept applies to the y-axis. As we take the distance h and let it approach 0, this distance, this change in y, becomes closer and closer to the y1 value, which is f of a. Now here I have 4 different notations for the derivative. It's very important to understand the different ways you could write the derivative to avoid confusion. I want to focus on this last one. The way I have it written down here is I have the f hanging down. Now I have it written that way because the d over dx acts as what is called an operator. So to explain what an operator is, I'm going to give a very simple example. Consider you have a simple addition problem, 2 plus 2, or a multiplication, 2 times 2, or a division, 2 divided by 2. This addition sign is operating on these numbers to the right and left. The multiplication sign is operating on the numbers to the right and left, and the division is doing the same thing. Over here, the d over dx is operating on the function f. Now to see how d over dx operates on the function, what we're going to do is first rewrite the function x squared over 6 into 1 over 6 times x squared. Okay, these are equivalent. What we do is we take the exponent and we drop it down to the left. So it's 2 times 1 over 6. And then we subtract 1 off the exponent. So it's going to be 2 times 1 over 6 and then x to the first. When we simplify this, we get 1/3 x. This 1/3 times x term, this is the derivative as a function. So let's pretend we didn't have this x equals 4 in the bar here. If we just wanted the derivative of the function f, this would be the derivative of the function f. This is known as the derivative as a function. So essentially what we've done was we've created a new function from the old one. The old one was x squared over 6, and then we've operated on this x squared over 6, and we've created a new function 1 over 3 times x. If we plug in a value into this new function, we get the slope of the line, or the derivative more specifically, at the value down here. So if we plug in 4 into 1 over 3x, we get 1 over 3 times 4, which is just 4/3. Now what that 4/3 means is that if we take the function x squared over 6 and look at the point 4, the slope of the line at the point 4, when the change in y and the change in x are very, very small, that slope is going to be 4/3. So the 4/3 is the slope that relates to the x squared over 6 function. We just use the 1 over 3x function to help us find slopes in the x squared over 6 function. And just another note on notation, down here I have the f up in the numerator, whereas over here it's hanging off, but it still means the same thing. For the dy over dx, you can have the y up here, or you could have it hanging off as well. It all means the same thing. Now everything that we've done over here, the operation to the function f, where we got a resulting value of 4/3, that is the same thing as this notation up here. It's just a shorthand way of finding the derivative of a function at a point. Now just one final recap. Please keep in mind that these graphs are not drawn to scale. So we started with the function x squared over 6. We've operated on that function to come up with a new function 1 over 3 times x. We were concerned with the point 4, which lies right here at the point A. We plugged in 4 into the 1 over 3 times x, and we came up with 4/3. Looking back at this function, if we were to shrink the distance h very close to A, so in effect we're shrinking the change in y and the change in x very close to each other, the slope of that line at the point A equals 4 is going to be 4/3. One final note on notation. Here we have the change in y and the change in x. As we shrink these changes down infinitesimally small, the notation becomes dy dx. And that's consistent with the notation we have over here, dy dx. If you have any questions or comments, please post below, and thank you for watching.